Hello everyone and welcome to Robot Operating System version 2 Jazzy Tutorials. In this tutorial we explain the basics of the TF Frame Transform library and we explain how to write a frame transform broadcaster node that publishes frame transforms. To explain the main ideas of the TF library and frame broadcaster, we constructed a model shown over here. This model consists of three objects, or by using the ROS2 terminology, three links. The first object, represented by this red cylinder, is stationary, and the two objects rotate around it with a constant angular velocity. Furthermore, the two objects rotate around their own vertical axes. This type of motion is achieved by constantly broadcasting coordinate transforms. The transforms are broadcasted, or better to say, published by using a C++ program. If we click over here, the objects will disappear and their corresponding frames will become visible. And this animation clearly shows what's happening behind the scenes. We have three frames associated and rigidly attached to the corresponding objects. We have the base link frame, the first link frame, and the second link frame. The rotating frame are describing a circular trajectory. On the other hand, they are also rotating around their own vertical or Z axis. The broadcaster ROS2 node continuously calculates and publishes frame transform between rotating frames on one side and the fixed frame. Everything explained in this tutorial is of paramount importance for properly understanding the ROS2 programming language and for writing more complex ROS2 programs that can be used for standard robotic tasks. In this video tutorial, we explain how to write a ROS2 package from scratch and this C++ code that implements and embeds the broadcaster node. Here you can see the class of the node, and over here you can see the function that defines the transforms and that publishes them. In addition to C++ code and the ROS2 package, we have created a manual that thoroughly explains all the steps that you need to perform in order to properly implement this exercise. And here's the manual. The length of this manual is 10 pages. It thoroughly explains all the steps, and in addition it explains the basics of TF2 library transforms. A link to this manual, ROS2 package, C++ and Python files presented and developed in this video tutorial are given in the description below this video. Okay, let's start with explanations. First of all, here's a brief summary of everything that you will learn in this video tutorial. In this tutorial, we explain the basics of the TF2 library and coordinate frames. Then we explain how coordinate transformation between frames and links are defined and tracked by using the ROS2 TF library. Then we explain how to write a TF2 broadcaster node in C++. And finally, we explain how to simulate and visualize motion of links and frames in ROS2 Jazzy. For those of you who are not familiar with ROS2 and robotics, TF2 is a ROS2 transform library enabling us to track position and orientation of coordinate frames over time. By using a tree structure, TF tracks relative position and orientation of coordinate frames of a robotic system at any time instant. This library enables us to calculate relative positions and orientations of frames and geometrical objects. When we say geometrical objects, we mean points, vectors, quaternions, etc. These geometrical objects are associated with links and joints, or in real life with the gripper, with the body of the robot, etc. TF library, or better to say TF2 library, is one of the most useful ROS2 library, and you should carefully try to understand and to implement this example. Here's the license and the copyright notice. This document, develop code files, lesson video, and all the provided material are referred to as the learning material in the sequel. Number 1. The learning material is the ownership and the original work of Dr. Alexander Haber, who is the author of this lesson. Number 2, you have the right to use the learning material for personal educational use and strictly for non-commercial use. Number 3, the learning material should not be copied, redistributed, or publicly posted on public or private websites, code repositories, and social media platforms. Number 4, the learning material should not be reproduced manually or automatically using an algorithm or an AI model from this video and then posted on public or private online repositories. Number 5, unless allowed by the author, the learning material should not be used as lecture material on online learning platforms and in university courses. Number 6, unless allowed by the author, the learning material should not be used to train engineers working in companies or paid academic researchers. Paid academic researchers are paid students, paid postdocs, paid professors, etc. Number 7, the provided code files and learning material should not be used to train an AI algorithm or a large language model. And number 8, unless allowed by the author, the learning material should not be used to produce academic papers, student reports, or other related documents. Okay, let's start with implementation. First of all, open a terminal, click here, and search for terminal. And here it is. To implement the material presented in this tutorial, you need to have Linux Ubuntu 24.04. Do not use Windows Subsystem for Linux or WSL since you might have issues displaying graphics. Install Linux Ubuntu on a computer. If you have a Windows computer, then you can install Linux Ubuntu in parallel to the Windows operating system by using a dual boot approach. Let's verify that you have the proper Linux Ubuntu version. To do that, we need to execute this command. And you should see Ubuntu 24.04. This last number is irrelevant. That is, these two numbers should be 24.04. Next, you need to have ROS2 Jazzy Jalisco installed on your system. Let's verify that ROS2 Jazzy Jalisco is installed on your system. If it's not, then on the YouTube channel you have a number of video tutorials explaining how to properly install and configure ROS2 Jazzy Jalisco on Linux Ubuntu. Over here, we will execute this command. This command will list the content of the standard installation folder for ROS2 Jazzy Jalisco. And if you see something like this means that ROS2 Jazzy Jalisco is most likely installed on your system. However, we still need to perform several verifications. One of the most important verifications is to try to source, or better to say to execute, this setup.bash file from the installation folder. And if you don't see an error, this means that most likely ROS2 Jazzy is properly installed and configured. However, as a last verification, execute this command, and this command should print out the environment variable for the ROS distribution, and it should be Jazzy. If that's the case, then you can continue and you can implement everything explained in this video tutorial. If it's not, as mentioned previously, then follow our previous tutorial on how to properly install ROS2 Jazzy Jalisco. In order to correctly explain the main purpose and the use of the TF library, we need to explain how coordinate frames are related to each other from the mathematical point of view. As explained in our previous tutorials, we associate frames with links and joints of a robotic system. By using the URDF language, we associate a frame known as a link frame with every link. This frame is fixed to the link and moves as the link moves. Depending on the type of the joint supporting the link, see our previous tutorial, the motion of the link frame can be pure translation, pure rotation, or combination of rotational and translational motions. From the mathematical point of view, we express this motion as translation and rotation of the link frame with respect to a link frame of the parent link in the URDF kinematic change. To illustrate this, consider this figure. This figure shows two frames in a 2D space. We have frame 1 and frame 2. Here, for presentation clarity and brevity, we assume that 2D space and only rotation around a single axis. However, everything explained in the sequel can be easily generalized to the case of frames in a three-dimensional space, as well as to frames that are not only simply rotated around certain axes, but we can also consider complete 6 degrees of freedom. In this figure, we assume that frame 1 is attached to link 1 and represents the link frame of link 1. Similarly, we assume that frame 2 is attached to link 2 and represents the link frame of link 2. Links are not shown here for clarity. As you can see from this figure, frame 2 is translated and rotated with respect to frame 1. The translation is represented by the vector d, and rotation is represented by the rotation angle theta or theta, however you like to pronounce it. By knowing d and theta or theta, we can completely transform coordinates of any point from frame 2 to frame 1. This is because frame 2 is rigidly attached and moves together with the link. That is, any point or geometrical object on the link associated with frame 2 can be mathematically expressed in the frame 1 of the previous link. And that's the power of the TF2 library. TF2 library keeps track of these transformations, and it enables us to quickly mathematically calculate the coordinates as well as the orientation, or better to say the pose, of certain geometrical object such as point, body, quaternion from one frame to another. To illustrate how transformations are written from the mathematical point of view, consider this figure. Over here, we assume that there is a point P in the frame 2. Assume that the vector B is a vector that connects the point P of link 2 or frame 2 with the origin of frame 2. The origin of frame 2 is denoted by O2. This vector moves as frame 2 moves. That is, it rotates and translates together with this frame. Now, notice this angle phi. This angle phi is always constant in frame 2. However, the angle theta, which is the rotational angle of frame 2 with respect to frame 1, can change. Assuming that the translation vector d is known, assuming that the angle of rotation theta is known, assuming that the angle phi is known, and assuming that the length of the vector b is known, our goal is to express the coordinates of the point P in the frame 1. That is, we want to find px1 and py1, which are the projections of the vector P in the frame 1. From simple geometrical analysis, it follows that these projections are given by these two equations. These two equations are relatively simple. Let's analyze this case and let's explain how px1 is found. Obviously, px1 is dx1 plus b and then cosine of this angle. That is the cosine of theta plus phi. Similarly, py1 is dy1 plus b sine of the angle, which is equal to theta plus phi. Simple as that. And that's precisely these two equations. That is, the main message is that by knowing how two frames are rotated and translated with respect to each other, we can compute coordinates of points in one frame with respect to another frame. This enables us to perform calculations for performing classical robotics tasks, and the TF library keeps tracks of all these transformations, and later on we can use these transformations to quickly express coordinates of a point from one frame to another frame, as well as the pose and other geometrical transformations. Next, let's explain the basics of the TF2 library, and let's explain the basics of TF2 transform stamped message that will be used in our C++ code. The purpose of the TF2 broadcaster is to define and communicate messages containing information about the translation and rotation of two coordinate frames with respect to each other. The TF2 broadcaster can be embedded in a ROS2 node, as we will do in our C++ code, and node can be used as this broadcaster. The broadcaster sends messages through a topic, and for dynamic transforms we use the TF topic, and for static transforms we use TF static. The dynamic frame transforms are created by creating an object or a message of the type geometry messages message transform stamped. This message consists of several components, and here are the components. The first component is the message header, and the type of this message is std messages message header. This message consists of two fields. The first field is the type built-in interface message time. It's used to define a timestamp of the transformation message. That is, with every transform between two frames, we associate a time, since these transformations can change over time. The second field is of the type string. This field is used to specify the name of the parent frame. These two fields have standard names which are built-in interface message time, and then we call it stamp, and we access it in a C++ code by typing .stamp, and similarly to access the frame or to define the frame ID of the parent link we simply use frame ID. The string defining the child frame name. This is the second component of our transform stamped messages. The standard name is string child frame ID. So let's explain this on our example. If we go back and if we look at this figure, frame 2 is a child frame of frame 1. On the other hand, frame 1 is the parent frame of frame 2. And when defining the time-stamped message or transform stamped message, we need to specify the parent and the child frames. And the third component of the transform stamped message is the message defining the translation and rotation. This type of the message is geometry message transform. This message contains two messages. The first message defines the translation and is of the type geometry messages message vector 3. That is, it's simply a vector. That's our vector D over here. And the second message is a message that defines the rotation. The rotation is expressed in quaternion and is of the type geometry message quaternion. Okay, quaternions are a little bit more advanced mathematical concepts, and they're extensively being used in guidance, navigation, and control, as well as the rigid body mechanics and dynamics. Here, we are not going to go too deep into definition of quaternion. However, you can easily calculate a quaternion which defines the rotation. That is, it defines the rotation axis and it defines the rotation angle by simply specifying the angle theta. You can specify the angle theta in radians, or you can convert radians or angles to radians. And this is the second message. That is, the third component of our transform stamp message actually defines the translation and rotation. Translation is expressed simply as a vector. On the other hand, the rotation is expressed by using quaternions, and we can compute quaternions by using a single C++ function. After defining the message transform stamped, we broadcast it by using the object of the type TF2 ROS transform broadcaster. Note that we can transmit the TF messages by using a static or dynamic broadcaster. The static broadcaster is used to send transform messages that do not change over time. They're sent through the topic called TF_static. On the other hand, the dynamic broadcaster is used to send transform messages that change over time. They're sent through the topic called TF. In this tutorial, we use a dynamic broadcaster. Then, as mentioned previously, the frames and frame transforms form a tree structure. An example that will be thoroughly explained and created in this video tutorial is shown over here. And here you can see a tree structure. That's precisely our example from the beginning of this tutorial. We have the base link, which is fixed. Then we have the first link, which is a child of the base link. And then we have a second link, which is again the child of the base link. On the other hand, a node can also listen and receive transform messages. We will not cover this topic in this tutorial, and it will be explained in our future video tutorials. Okay, let's go back to the implementation. The next step is to install the necessary ROS2 packages or verify that they are installed. In this tutorial, you will need several ROS2 packages. Most likely these packages are already installed if you have followed the instructions for installing the full ROS2 Jazzy desktop version. However, it's still a good idea to try to install them to make sure that they exist on your system. We will need the Robot State Publisher package for the Robot State Publisher node. We will also need the RViz package, and this package is used to visualize the geometry and motion of a robot by using a simple graphics user interface shown at the beginning of this tutorial. We will also need the TF2 package. Before you install the package, make sure that you source the environment or that you're in the terminal that we opened previously, and then over here in this terminal type sudo apt update and then type sudo apt upgrade and press enter. And this should update and upgrade all the packages. Remember, whenever you want to install a new package or new program on your Linux Ubuntu, make sure that you run these two commands and such that everything is up to date. And over here you need to be patient, and here we are. Next, let's just in case once more source the environment, and then let's start with installation. So let's first try to install this package, and you can see that this package is already installed on my system, and this might be the case for you also. So next, let's go with the second command with RViz, and over here let's install TF2. Okay, and this is all we need to have. Now, let's now learn how to verify if a package is installed on your system. To do that, you simply run this command, and you can see the complete list of packages. However, this list is too long, and let's learn how to filter out. For example, let's say that I want to search for a package called RViz. I can simply run this command, and over here with the grep and this vertical line, I will filter the result, and I'm going to filter it out according to this string, and the name is RViz. And you can see all the packages which contain RViz in their name. And in this way, you can verify that packages are installed. The next step is to create the package URDF, C++, and launch files. And let's learn how to do that. Now, to practice this sourcing the environment, let's close this terminal and let's open a new terminal. And over here in this new terminal, as always, whenever you want to start playing with ROS2, you need to source or to execute this configuration file. So let's do that. Next, let's go to the home folder, and over here in the home folder, I'm going to create two folders. These two folders will be created by using this command. The base folder name is demo_ws, where ws stands for Workspace, and inside of that folder, I'm going to create the source folder. Okay, now let's navigate to the demo Workspace folder, and inside of this folder, we have the source folder. The source folder will contain the source of our package. So let's navigate to this folder, and inside of the folder, which is currently empty, we are going to create the basic package structure. When I say the basic package structure, I mean the basic files and folders. To create the basic package structure, we need to execute this command. Okay, so let's analyze what this command is doing. We call ROS2 package create, then we specify the build type, Here we are going to use CMake build type, and then finally we specify the name of the package. And remember, this command should always be executed in the source folder, and press enter. And now let's analyze what happened over here. You can see that several files and folders are being created. Okay, so let's list them and let's see what they are. Here they are. Aha, we have a new folder. Note that the name of this folder is precisely the name of our package. So let's navigate to this folder, and inside of this folder we have several files. CMake list file is the CMake configuration file that governs how the package is being compiled and built. Then we have the include folder, which can contain the include files. Then we have another package configuration file, and finally we have the source folder. This source folder will contain the C++ implementation of our broadcaster. On the other hand, in this folder we will need to create several additional files and folders. Okay, we need to create launch, URDF, and configuration folders. So let's execute this line and let's see what has been changed. You can see now configuration folder, you can see the launch folder, and you can see the URDF folder. The configuration folder will contain the rviz configuration file. This file will be created later on. Then we have the launch folder. The launch folder will contain the Python launch file. Launch files are used to define how ROS2 nodes are being started and executed. Furthermore, you can start several nodes with a single launch file. Then we have the source folder, which is explained previously, and we have the URDF folder, and this URDF folder will contain the model of our system. The next step is to create the URDF model of our robot. To do that, we need to navigate to the URDF folder, and inside of this folder we need to create a file called model.urdf. In this video tutorial I'm going to use Visual Studio Code to create this file. However, you can use any other editor. If you don't have Visual Studio Code on your system and you want to use it, then I created a separate video tutorial explaining how to do that. You can find that tutorial on my channel. Here I'm going to start Visual Studio Code, and I'm going to create a new file. File, new file, and let's call the file as model.urdf. This is the name of the URDF file. Press enter and store it inside of the URDF folder. Let's double check that the name of the file is correct. Since a lot of people are making this error, it should be model.urdf. Perfect. Here, to save time, I'm going to simply copy and paste the content of the file. Here it is, and let's explain this file. First of all, over here we need to specify that this is an XML file, and we need to specify the version. Over here we wrote a simple comment, and then over here we start the robot tag, and at the end we end the robot tag. We call the robot as simple robot. Here is our first link. We start the link tag and we end the link tag. We call the link as base link, then we start visual, and then we end visual. Then over here we start geometry and geometry. Our link is a simple cylinder with a length of 0.1 and a radius of 0.2. Then we need to specify the location of the origin frame of this link, or better to say the center of this link, with respect to some world frame. This some world frame is actually the rviz world frame. Here we are centering the link at the world frame. RPY means here roll, pitch, and yaw, and this parameter defines the roll, pitch, and yaw rotation of the center of the link, or the frame associated with the center of the link with respect to the world frame. And over here X, Y, and Z represent translation in the X, Y, and Z directions. Here we specify material name, it's red, and we give it the color code. This is the standard RGBA color code, where A is the transparency. Since this is red color, we will have 1, 0, 0, and then 1. 1 here means that it's completely non-transparent. And then we end material, we end visual, we end link. Next, we specify joint 1. Joint 1 is a joint associated with the first link and rigidly attached to the first link. First of all, we specify the parent link. It's the base link defined here. Then the child link is actually the first link. And then over here, we specify the origin. The origin of this link is defined with respect to the origin of the world frame. And the origin is defined like this. There is no roll, pitch, and yaw rotations. And over here, we have translation. I have translation of 0.5 in the X, 0.5 in the Y, and 0 in the Z directions. And over here, I'm specifying the rotational axis. It's the Z axis. Note over here that the type continuous means that this joint can continuously rotate around its axis. Then finally, we specify the limit. This is the limit torque of 300, and this is the limit velocity, and that's it. Next, we define the first link. We specify the link name. We specify the visual representation. We specify the geometry. It's a box. We specify box dimensions in the X, Y, and Z directions. And then we specify one very important parameter. Over here, we specify the origin of the link. And origin of the link is actually placed at the origin of joint 1. Consequently, we don't have roll, pitch, and yaw, and we don't have translation. And then over here, we specify the color for the blue color, or the code for the blue color. We end material, we end visual, we end link. Next, similarly to joint 1, we define joint 2. Its type is continuous. We specify the parent link, it's the base link. We specify the child link, it's the second link. We specify the rotation and translation of the frame associated with this joint with respect to the world frame. Here are the parameters, and we specify the axis of rotation. It's the Z axis. Then we specify the limits, the limit torque and limit velocity, and that's it. And finally, here's our second link. Here's the visual representation. Here's geometry. It's a box with these dimensions. Here is the origin. The origin is placed at the origin of joint 2, and over here we specify the color code for the green color, and that's it. We end the link and we end robot. And let's save this file and let's continue. The next step is to write the launch file. To do that, navigate to the launch folder, and inside of this folder you need to create the launch file. The purpose of this launch file is to define how nodes should be started and to start nodes. That is, we will start several nodes with a single line. That is, we will execute a Python code that will start all the nodes. So let's write this file. Over here is the content of the file. The name of this file should be display.launch.py. Here I'm going to copy everything, and then I'm going to paste the content of this file. However, first of all, we need to create the file. The file name should be display.launch.py. So let's go to the Visual Studio Code, click on File, New File, and call the file as display.launch.py. Make sure that the name is correct, display.launch.py, and save it inside of the launch folder. That is here, and create file. Again, display.launch.py, since this is the Python code, and here's the content of the file. Again, let's explain the main purpose of this file. This file will start two nodes. It will start the robot state publisher node, and it will start the rviz node. Note over here that the robot state publisher node might not be completely necessary. However, I noticed that for some reason rviz had issues running everything without that node. Consequently, I defined how this node should be started, and I started it. First of all, we need to import the necessary Python libraries and packages. Then we need to specify the name of the package. Note over here that this name is precisely the name of our package. That is the name of the folder. Then we need to specify the relative path of our model.urdf file with respect to the package folder. And here's the relative path. Then we do the same thing for the ROS configuration file. Note over here that we still didn't create this ROS configuration file whose name is config.ros. This file will be created later on and it will be stored in the config folder. That's precisely the folder we just created. Then we define a function that defines how nodes should be started and starts nodes. First of all, we retrieve the absolute package path. That is, this is the path to this folder over here. This is the path, okay, to the base package folder. Now, we can do it automatically in ROS2 and Python by typing this command. Then we simply join the package path with the relative path of our model URDF file. We do it like this, and we define the URDF model path. And note here that this is the absolute path. Then we define the absolute ROS configuration file path. Again, we join the package path with the ROS relative path, and we store the result in ROS config path. Okay, here for verification, we print the URDF model path. Then we load the model URDF file. We store it in the robot description. Then we define this parameter, or better to say a dictionary. We specify robot description and we pass the URDF file. And over here, we explain how robot state publisher node should be started. Okay, we use this function. We specify the name of the package, the name of the executable. Note over here that these are the standard ROS2 packages. Then we specify the output should be screen. Then we specify the parameters, and we specify the absolute URDF model path. Note over here that we are also passing the URDF file as a parameter. And finally, we define how the ROS node should be started. The ROS node is used to visualize everything. We specify the package name, executable, name, where it should be started, and we specify the arguments. Finally, we combine everything and we return. We say, you need to start robot state publisher node and ROS node. So let's save this file and let's continue further. The next step is to implement our C++ files. Again, let's go back to the terminal, and these two files should be placed inside of the source folder. So let's create these files. Click on File, click on New File, and let's call the first file as test1.cpp. Note over here that the file needs to have the extension C++ or CPP, since this is a C++ file. So let's go back to the demo robot. Let's go to the source folder and let's save this file. Again, to save time, I'm going to simply copy and paste the content of the file. I will copy this, then I will go here, and then I will paste the content of this file. Okay. And let's explain, first of all, the main purpose of this file. The purpose of this file is to implement a C++ TF2 broadcaster. The broadcaster class should define the coordinate transforms between second link and the base link, as well as the first link and the base link, and should publish these transforms. And then later on, these transforms are read by the ROS node and they're displayed on the screen. First of all, we need to include the necessary header files and libraries. First of all, we need the RCL CPP and this header file. RCL-CPP is the ROS2 client library for C++ that is included with any standard installation of ROS2. RCL-CPP provides the standard application programming interface or API. Then we need a header file for quaternion object defining the rotation. We need to include this. Then we need these two TF2 header files. Then we need this file for math functions. We need this file for thread, and we need chrono for time. And then finally we use this code line to simplify the notation. Here is the class implementation for embedding the broadcaster node. This class inherits from the node class. Consequently, we name the class and we specify public RCL-CPP, meaning that this class is inherited from the parent class node. And this is a standard practice. Namely, the node ROS2 class provides a basic functionality of every node. And if we want to add additional functionality, we will simply inherit or define a class that's being inherited from this class. Over here, let's start with this constructor. Here, we need to call the constructor of the parent class, and as a main argument, we specify the name of our class. It's going to be broadcaster node, or the name of our node. After calling the constructor of the base class, here we are printing on a terminal that we are starting the broadcaster node, and then over here we instantiate the broadcaster object. Broadcaster object is defined over here. It is of the type TF2 ROS transform broadcaster, and it's actually a pointer to this data type. And here it is. Then we instantiate it, and we simply type this over here, meaning that we are passing this particular class. Then we need to instantiate the timer and bind the broadcaster function. Here's how the timer is being declared. Actually here's how the timer is being declared. And let's explain the purpose of the timer object. The purpose of the timer object is to make sure that certain functionality is being executed with a certain period. In this case, by using this create volt timer and by specifying 100 milliseconds and by binding our broadcaster function, we are ensuring that with a period of 100 milliseconds, our broadcaster function is being called. That is, every 100 milliseconds, we will perform something, and that something is defined in our broadcaster function, which is declared over here. Now, here is the implementation of the broadcaster function. Let's explain the basic idea. Here, the broadcaster function will define two transform stamped messages, and these transform stamped messages will explain and tell to ROS2 and RViz how first link frame and the second link frame are being transformed with respect to the base link frame. And that's the main idea. In this file, we are going to simply pass constant transforms. And then in the next file, we are going to pass dynamic transforms. Okay, so first of all, here we are creating two transform stamped messages. We add the timestamp like this. Then we specify the parent and the child frames. For the T1, the parent frame is base link, child frame is first link. For T2, the parent frame is base link, the child frame is second link. And then over here, we need to define two things. We need to define translation between frames and rotation between frames. In the case of T1, here is the translation, X, Y, and Z directions. And in the case of T2, here is the translation, X, Y, and Z. Next, we need to specify the rotation. To specify the rotation, we need to use quaternions. Here we declare two quaternions, and then over here we are simply setting the components of the quaternion on the basis of desired rotation angle. This function setRPY sets the roll, pitch, and yaw angles, which are rotations around X, Y, and Z axis. And then here I'm simply rotating around the Z axis for the constant angle, and then over here I'm simply filling the fields of T1 transform rotation by extracting the quaternion components. Quaternion is a four-dimensional vector. It has x, y, and z and w components. And I do the same thing for the Q2, that is for the rotation of the second link with respect to the base link, and then I extract the quaternion components, and here I'm sending or broadcasting the messages, and that's it. And I'm simply printing the messages in the terminal, meaning that I'm printing only a single message, TF message broadcasted. Note over here again that over here, after we fill in all the fields of T1 and T2, we simply send or publish or broadcast these messages. And that's it. And here's our main function. It's relatively simple. Over here, we call the init function. Note that before using the RCL CPP API, we must initialize it by using this function. This should be done once per process, and this function will initialize any global resources that are necessary for the middleware and client libraries. Then after that, we need to instantiate our node. I call it as a test node, and over here we simply spin the node, that is, we set everything in motion. This spin function will do several things. It will make sure that the timer functions and all the bindings are being done properly, and it will govern everything. And then finally we shut down. The purpose of this function is that if, for example, a user presses Ctrl C, then before this code is being end, the memory will be released, and that's it. Let's save this and let's continue. Next, let's define another C++ function, and this time we are going to send transforms that will dynamically change. Note over here that the second function will create the motion that you have seen at the beginning of this tutorial. So let's click on File, let's click on New File, and let's call it as test2.cpp. And then let's save this file inside of this folder, and over here, let's do the following. Here, I'm going to simply copy and paste the code. Here it is. And then let me paste this code, and let's go through this code. Okay, the include section is exactly the same as the include section of the previous code. And here's the class definition. This part is the same, that is, I'm using the same constructor and the same broadcaster function, as well as the broadcaster object and the timer object. So everything is the same. However, here comes the main difference. Here, in addition to these private objects, I have these private member variables. They are angle 1, angle 2, radius, and delta angle. So let's explain their purpose. Here, we are going to create a motion on a circular trajectory. That is, our two links, that is, let me just show you the links. Here they are. First link and the second link will actually move along a circular trajectory around the base link. And to do that, we need to define two parameters. We need to define the radius of the circle, and we need to specify the angle on that circle. That is, angle defines the angle that a link creates with the base link. Okay, and here initially angle is 0 and the second angle is pi over 4. Here's the radius and here's the precision of rotation or the increment. What will happen here is that the timer object, by calling the broadcasting function, will every time step, that is every 100 millisecond, publish a new TF transform, and this new TF transform will create motion. Okay, so let's see the implementation. This part is the same. We declare two messages. We fill in the time step, the base and the first link, as well as the base and the second link relationship in the tree are the same. And then over here comes the magic. Here we define the translation between frames. That is, T1 defines translation between the first link and the base link, and here's how X and Y components are being changed, and this creates motion on a circle. We do the same thing for the T2, and next we need to define rotation. We declare two quaternions, and let's see what's happening over here. Here, First link frame as well as the second link frame will also rotate around its own z-axis, and consequently we specify here the angle of rotation, we fill in the components for rotation, and that's it. And then finally we broadcast the message, we increment the angles. That is, every 100 milliseconds we increment these two angles for this offset, and then we print the message in the terminal, and that's it. The main function is exactly the same. We initialize, we instantiate, we spin, and we shut down. Simple as that. Let's save this file and let's continue. In order to correctly compile and build everything, we need to modify two additional files. We need to modify the package.xml and cmakeLists file. So let's learn how to do that. To do that, I will go back to Visual Studio Code, then click on File, then click on Open File, then I will go to this folder and I'm going to edit package.xml. Okay, now over here, after these two lines, let's make some additional space. And in order to save time, I'm going to simply copy and paste the modifications and include them over here. And let's explain what these lines will actually do. First of all, go back to your test1 CPP or test2 CPP folder, or actually file, and go at the top. And notice these lines, this line, this line, this line, this line. These lines are actually referring to the corresponding packages, to RCL CPP geometry message, TF2 ROS, and TF2 geometry message. In addition to this, note over here in the launch file that we used RViz and we used the robot state publisher, and consequently we need to add these dependencies, and we do it like this in the package.xml. Executive dependencies TF2 ROS, TF2 geometry message, RCL CPP. This corresponds to C++ code, and then we have RViz and robot state publisher from our previous code. Okay, good. Or actually from our display.launch file. Let's save this file and let's save all the other files and let's continue. The next important modification is the modification of the CMake configuration file. So open that file, that is open cmakelist.txt, and over here after this line and before if build testing, add some empty space. So what are the lines that we need to include? Well, to save time, I'm going to simply copy and paste the lines that I need to include. So here they are. Let me now go until the end. Let me see where they are. Here they are. Okay, let me copy this and let me go here and let me paste everything, and let's explain what's happening over here. Again, going back to the test2 or test1 CPP, note over here these header files. So you need to tell to your CMake build system that your code depends on these packages and the corresponding header files. So we write find package TF2 required, find package TF2 geometry message required, geometry message required, RCL CPP required. Good. Now we solved this issue. Let's save this file. Then, since we are building everything, we need to define the executable names. So for the test1.cpp, which is inside of the source folder, we need to specify the executable. The executable is test_tf1. We do the same thing for the test2 CPP. For test2 CPP, the executable is test_tf2. That is, when we run the code, we are simply going to type ROS2 run, name of the package, and name of this executable or this executable, and these executables are actually linked to these source files. Actually, everything is being compiled at that point, and we are going to run a compiled code corresponding to this source file. Then we need to install the target dependencies for these two executables. Our test TF1 depends on TF2 ROS, TF2 geometry messages, and RCL CPP. This will help during the linking process, and we do the same thing for the executable test underscore TF2. We link the corresponding files, right? And then we need to install these targets. That is, we need to install the executable test TF1, and we need to install the executable test TF2, and here we specify the executable folders. And then finally, at the end, we need to tell to our CMake system that our files, or actually to say that that we have created additional folders which are launch, RDF, and config, and the CMake system should search for source files and other files inside of these folders. Note over here that every time you create an additional file or folder inside of this package folder, you need to actually write it down over here. Since we created launch, URDF, and config, we need to write them down. Note over here that we didn't write source and the other folder, which is basically include, since they're understood automatically that they're inside of this folder and you don't need to add them. So let's save this file and let's continue further. The next step is to build everything. To build everything, you need to go one step back and another step back. That is, you need to go to the base folder, right? You need to go here, and inside of this base folder, you need to do the following. First of all, it is suggested that before you build everything, that you need to add or to check if everything is being installed. To do that, you need to install this very useful program, Python 3 ROS2. So execute this line to install it, and then over here you need to initialize it and you need to update it. So initialize it, ignore the error if you see it, and update it. Here it is. Okay. And then finally, let's double check that everything is properly installed. We can do it like this. And if everything is being written correctly, you should get this message, all required ROS depths installed successfully. And finally, we can build everything. Make sure that you're in this base folder and make sure that this is the terminal in which you have sourced the environment. So this is very, very, very important step. Now, a good suggestion over here is to do it once again. So type this command once again to make sure that setup.bash file is properly being sourced. Okay, and now we can build everything. So how do we build things? Well, we build things in two ways. You can simply type this command, and then you need to specify the name of the package. Over here, we are using the colcon build system, and then over here, you're specifying that you want symbolic links installed, and then you specify the exact package name, which is demo_ROS. Here, you can also just run colcon build, and this will build everything. However, disadvantage of just using colcon build is that if you had hundreds of packages inside of this folder, everything will be built from scratch. Over here, you're just building the package that you created, and let's press enter, and let's hope that there will be no errors. Let's just pray, no errors. Excellent. Next, let's open a new terminal and let's start RViz. To start RViz, you first of all need to source the overlay. That is, you need to source the setup.bash installation file in the created package. So run this, and then finally run the launch file by executing this command. So you type ROS2 launch, then the name of the package and the name of the executable, press enter, and voila, RViz started. However, nothing is being displayed. Well, this is perfectly normal since we didn't set up the RViz and we didn't create the configuration file. So let's first of all properly configure RViz. To do that, click on add, go down, and over here click on by display type and find robot model. I always have issues for some reason finding the robot model over here. However, here it is. Okay, click on OK, then expand robot model, then display description topic, and then over here click on robot description and something will appear. However, the links are not properly being displayed. That's perfectly fine, so don't worry about it. So then here as a fixed frame, let's use our base link. Base underscore, let me just type it correctly, base link, and now you see that the base link is properly being displayed. However, other links are still not being properly displayed, and that's perfectly fine. There are no errors over here. Next, let's add an additional thing. Click on add, and over here find TF. So we want to display our TF frame. So click here, and of course you will not see them since everything is being covered. Note over here this error. So let's see what is this error, and let's see what's written over here. No transform from first link to base link and from second link to base link. And that's perfectly normal and expected. Why is that? This is because we didn't run our C++ code. Perfect, no issues. Next, let's save this configuration. To do that, click on File and Save As. However, let's make sure that we save the file properly. Go back to Visual Studio Code, open display.launch file, and copy this name, config.rviz. Then go back to rviz, click on File, Save As, and here you need to save this file in the proper folder. Go back to the BaseWorks folder, go to the source, go to demo, then go to config, and over here paste the file name and click on Save. The purpose of this is that next time we start RViz, we want to make sure that RViz starts with this configuration such that we don't have to every time adjust RViz. Go back to the RViz terminal, press Ctrl C. Then go back to the original terminal and build everything such that we can apply the changes. Then go to the RViz terminal, source everything again, and then display everything. And now voila, magic happens. Everything is being displayed properly. The final step is to test our code. To test our code, open a new terminal. And then inside of this terminal, you need to do the following. You need to actually again source the overlay by executing this command, and then let's run the first code. Now I'm going to copy this and I'm going to paste, and let me now do this such that you can see what happens over here with RViz. And once I execute this line, I'm going to execute the executable test.tf1, and let's see what happens. Bang! You see now what happened. So these frames are being properly adjusted. That is, their position is precisely the position being specified in our C++ code. And we can verify that if you go here and look at the translation. So let's see, 0.5, 0.5. This is basically the first link. Click over here to turn off this, and you can see the links. However, click here and click on Show Names to see all the names. So let's see the first link and the base link. So let's see where the coordinate system, so it's somehow like this. So you see the first link, 0.5, 0.5. The second link is basically 0, minus 0.5, minus 0.5. And let's see the rotation. The rotation of the first link is, let's see it over here, is pi over 2, and you can see how the axes are nicely rotated. The same thing applies to the second link. Okay, so this is our first test. Let's save this configuration once more. Okay, this is very nice. And then let's now again click here and let's run the second one. Okay, to run the second one, you can simply press Ctrl C over here, and to run the second code, simply run this command. So let's do this. Let's go here and let's paste this and let's press enter, and voila, everything moves as expected. You can turn on and off the model like this. And if you do this, you will only see the links. And before we conclude this video tutorial, let's explain several important things. Sometimes you would like to manually debug everything, and let's learn how to do that. First of all, open a new terminal, and inside of this new terminal, let's again source everything. Here you're sourcing the ROS2 base, you're not sourcing your package, and then run this command. This command will actually create a graphical representation of our tree structure. So let's wait for a while and let's see what we have created. Inside you will see these two files. To open one of these files, simply type its name and type evince. Evince is a simple program for visualizing PDF files on Linux Ubuntu, and you will see over here, beautiful base link, first link, and you can see the transforms. Good. Next, let's echo the transforms. Press Ctrl C, and to echo the transforms or to display in the terminal what's happening, you need to simply execute this command. So you need to type ROS2 run, then you need to type TF2 ROS, and then the name of executable TF echo, then you need to specify base link and the first link, or the parent and the child link, and let's see what happens. You'll see all the information about your transformation. You will see time, you'll see translation, rotation in quaternion, rotation in RPY, a rotation in degrees, and you will see this matrix. So this matrix is a very important matrix, and this matrix is actually homogeneous transform matrix. Okay, that's all for today, and thanks for watching.